Alright, so now today we're going to deal with depth estimation, and I feel it's actually pretty simple. There just needs to be really right way of thinking about it. So I will make it probably pretty long, slow, but hopefully I will get all the ways of thinking right. So how it works? We're going to estimate depth binocularly. So we have like left camera, right camera, and there's like an object, and then we observe the object over here, right? It forms this nice triangle, and like because we constructed the robot, we know what's the translation between a left camera and right camera. Sometimes it could be, that they just like look a little bit inward or outward, like this, for example, my eyes sometimes look a little bit outward, but in general, in general, we just know what's the translation, what's the rotation between those cameras. We know how to translate those two coordinate systems. And then, so again, I mean, I feel like I'm painting this for like, 100th time, but it doesn't matter. Let's paint it even one more time. So left camera, right camera, what we see. So we see a triangle, right? Maybe this, here's the triangle, more or less. Here's the key point that we have found and matched based on its descriptor. And then each of those has like, so each of this is really in like a 3D coordinate, right? So this point over here, right, it has like sort of x, y, and either one if it's in this like when it's projected to the plane. But the true point, it has full coordinates in this like coordinate camera, right camera coordinate system, right? It's like x, y, and z is the depth. So this is what we care to estimate. This is the z, right, in the right camera. Let's call it zr. And then z in the left camera is this thing over here, right, the zl. And that's kind of similar thing, right? So this x and this y, it's kind of not the same, right? It's kind of scaled, but it's just two ways of thinking about really the same point, right? So either as this or like the thing in the bottom. So yeah, that's the strategy, roughly speaking. And so when I wrote the code, I understood the problem kind of less. So I just sort of followed an equation and it worked out for me. Now I see there's a slightly better way of understanding it. Let me just show it to you real quick, right? So because we assume our R to be identity, we don't really rotate between the cameras, and the position of the left and right position of the left and right camera is just translation to the right, so if we want to go to right camera from left, so sort of like position of right in left, and that's so this like identity 0, 0, 1, and then here we have x, right, so that's like 2 and 0, 0, 0. So in other words, the translation matrix is, sorry, the translation vector is 2, 0, 0. So translation of right camera in left, so just 2 to the right. So, and then this makes us, so what this means is that like generally things that are on the same yeah, so basically matched points should be on the same height between left and right. So if we see a point that's like mismatched height wise, so on the x-axis, it's kind of like a sign of bad matching, right? So just like a small exercise. And then just looking from the top, right? So so we have left camera over here, and we have right camera over here, and then we have like a image plane here and image plane here. This is 1, right? 1. This is 1. Then we have an object here. So left and right. Here we have like a distance of let's call it t. and then here's this, and here's this, right? And then so in here, in the right camera, the thing is going to have, let's call it R to the left, right? So here's like R, and then the thing here, so let me just draw it just to make it super clear, right? So this is the middle of the picture, and then there's going to be an object, and it will be R to the left. So that will be R to the left. So X will be sort of minus R in the right camera coordinate, and vice versa. So here like L to the left, and let's call this thing D over here, right? And then if we draw it again like this, here we see that this is T and this is D. This is H, and this is 1. So from the triangles being similar, we can see the following. So H plus 1, which is the height of the big triangle, divided by T is the same as proportion of H to D, because those are just like scaled up the same triangle, right? So now we solve for H. So what we have is HD plus D equals HD, which means D is H times T minus D, and then H is equal to D divided by T minus D. Alright? Alright? H plus 1 over T is like H to D, so HDD, HT, then we solve D, T minus D, makes sense, and then H is this. And then let's call this like, so T is equal to like D plus R plus R. So this is like R plus R, right? And then T minus R minus R. So we just have, and T is constant. So we just like take this R and R, and that's it. We just have our depth. We just have this. So we could do this, no problem. Well, just to be super clear, right? Don't have this, we have this, right? Actually, it's like H plus 1 and so on. Yeah, plus 1, so that's like T minus R plus R plus R plus R over R plus R equals, so H plus 1, which is what we care about, which is depth for the point, right, is T over R plus R. So very easy thing, right? 2 over whatever is the difference between those, right? So very easy equation, hope it makes sense. But I didn't know that, so I did something slightly more complicated. What I did is the following. So I did where is my intro to VSLAM book? PDF, this thing. Yes, 6.5, right? So here they have a bunch of equations, and let's just walk through these equations together. So basically they say Similar to the previous section, consider images I1, I2. Transfer matrix from to the right image is T. So it has like this R component and this little t component. So we do like from O1 through P1 we see the point, and then through O2, from O2 to through P2 we see the point as well. And then we write S2 times X2. So again, X2 is just like a direction, and then we scaled by S2, and this should give us point. And then starting from this other point, right? So if we take X1, make it S1 long, and then if we just rotate it, right? And like it doesn't matter if we first multiply by S1, it's just a scalar, and or like we first rotate. So S1 times X1, right? Just like literally starting from this other thing, rotated, bam, which in our case is, by the way, nothing, plus t has to be the same thing, right? So again, like this, scale by S2, rotate, translate the whole origin, and this has to be the same thing, right? So so this is where this equation comes from, just like same as usual transformation of, I mean slightly different because not homogeneous, right? But like in general that's the point. And then second thing that they use, so what we will use right now is this thing called cross product. So cross product is, it has a lot of depth, it has a lot of like important implications and so on, but like how usually it's introduced, is also introduced in high school, is if I take vector A and B and those sort of give me like a parallelogram, then or like is it called parallelogram? Yeah, parallelogram, exactly. So this is the area of the parallelogram, like A times B. I don't need to know like what's this angle. A cross product B, absolute value of this gives me area of this parallelogram. So that's pretty cool. And then it also implies, right, like if A times B is like just the same thing, right? A cross B is the same thing, the parallelogram is 0, right? So this geometric interpretation makes sense. And like notice how it's like also, so A cross B gives you vector, so it's an operation that takes a vector and another vector and it gives you back a vector, and then area of this parallelogram is length of this vector, right? So that's important thing to notice. And then yeah, you have this like right hand rule, so where it points, right? So if you flip the B, it goes to the minus. So, and yeah, just watch this GIF together. So if it's the same thing, then it's 0. If it's not the same thing, this is sort of where the cross product is maximum. So then it's literally product of the lengths of the vectors, and then it's 0 again, and then now it's going to flip. So yeah, and it's just pretty deep because it just comes up naturally all over the place in the natural geometry. So it has so many different properties, but one property that I care most about is that the vector cross product can also be expressed as the product of skew symmetric matrix and vector. So we can take A and we can vec hat it, so vector hat it, like we can put a hat over it, and then it maps, it's a map from vector to matrix, and then left multiplying another vector by this matrix give us a cross product of the original vector A and then of the B, right? And this is how the matrix looks like, right? So it's like A 1, 2, 3, and then it's skew symmetric. So like when we transpose, it minuses. So that's how I remember. It's like A 1, 2, 3, and then minus, no minus, minus, and then you minus when you flip. So that's how it works. And then from this, let's just verify real quick that when we multiply or like when you compute cross product in this way, so we multiply by vector hat of the vector, then we get 0. So let's go to the blackboard. So I mean, and there's just like mathematical reasons and intuitions why this definition and not some other definition, but for now I just like take it for granted. So let me take a vector x, and then let's call it a, b, c. All right, and then x hat, it will be this matrix. So a, b, and c, and then c, b, a, and then minus, no minus, minus, and then no minus, and then minus here, and then just zeros on the diagonal. So if I do this times this, then what do I get? C minus b minus c, nothing, a, b minus a, nothing, and then I have a, b, c. So let's multiply. So here is minus cb plus bc, and then on this one I get ac, right, over here, nothing, minus ac, and then here I have minus ba plus ab. So I get 0, 0, 0. Awesome. So everything works. And now coming back to the trick from the book. So the trick from the book, we take this equation again, and now we will multiply by hat of the x2. All right. So we take this and this. This is just like epipolar geometry. So x2 times s is here, x1 times s is here, then rotated plus t has to be the same thing, right? So the lengths sort of have to agree. And now we do the following. We hat it, so we multiply it, left multiply it by hat of x2, so by this vector, and then we just verify that this has to be 0, and then we get an equation. And now we have to solve this equation. And then when we solve this, so notice, so this is, in our case, this will be identity, so nothing at all, but like this gives us 3-dimensional vector, then multiplied by 3 by 3 matrix, also 3-dimensional vector, and then this is 3-dimensional vector, 3 by 3 matrix, in all 3-dimensional vector. So we will solve for S1 with 2 3-dimensional vectors. So we will be able to solve 3 times, because it's like, it will be like S1 times like vector equals minus vector. So it will be 3 equations to solve. So and then if you spend enough time with those equations, you will be able to notice how if you reintroduce these constraints that we have in our specific case, where the rotation matrix is nothing, and it's not like in general VSLAM, it's just like in our concrete case, for our concrete example that we are building in simulation, right? It's just like R happens to be 0. So if you reintroduce this, and then if you reintroduce also this constraint that t in our case is just like the vector that goes right in x, so it's like plus 2 or something, like 2 meters of the span between eyes, and then 0, 0. So if you reintroduce this, then you will be able to reduce it back to those triangle equations that I have shown. So just like literally division of this, how far away are we between eyes, and like how far away on in those image coordinates are the points in the respective images, right? So you will be able to reduce it back. But yeah, as always, it's like, you know, easy math, but like you have to be really, really careful to really get every single thing right? So just be really, really patient and recompute those things. So now let's see how it works in practice, right? So if you look at GitHub, and then here's my repository. You go to VSLAM, and then you go to triangulation. So VSLAM triangulation, and then you have blah blah blah, basically what we were talking about. And then yeah, we have naive triangulation, and it's naive because it's, so here, like in this formula, we have just division by 0 potentially, right? And like I just literally get rid of this division by making sure just like not computing this, not dividing when the a is just too small, right? And like just for good measure, I also do it for b. No really reason for it, right? But that's the, yeah. And then if the solutions are too different, so you will get two solutions, right? And then if the solutions are too different, I just reject this and like just say, okay, I don't know what's the depth, and this is like this non-thing. And if the solutions look kind of similar to each other, then I take their average. So really naive way. So here's naivety, and here's another naivety. If we wanted to be less naive, then we would go for the triangle equations, right? And then this would enable us to get rid of this. And yeah, also maybe one naive thing is like that we literally iterate over points in the camera. It's just pretty slow in Python. There's for sure ways to vectorize this loop. I just wanted to make it easy to understand. So, and it's fast enough. So that's what I did. So let's see. So let's just, so I start actually from this exercise 03, full front end. And then in the original repo, it goes like VSLAM, lessons, exercise 3, full front end. And then I run it. I say live data equals true. So I run it. Let's see how it goes. Right. So so we see left eye and right eye, and then here's like you notice there's like a little bit of difference between those, right? And then when I go into, so there's like this front end thing, right? And this front end thing is what has the actual tracking. So yeah, so here's the entry point track. So this is the main function for this thing. Then it goes to post tracker track, and it goes to estimate new keyframe. And then in this estimate new keyframe, this is where we do the triangulation, just to get the first idea where how deep the points are. So yeah, here's the estimate keyframe. Let's go deeper, go inside. So we see like the feature matches, then we do a bunch of this coordinate transformations, and then finally we go into knife triangulation. And then what I'm going to do, I'm going to place breakpoints, and we're going to restart the system and see what kind of data we are getting in there. So start the system. All right, and we're in. So let's look at things one by one. So x1, points in camera 1. So in camera 1, so that's left, camera 2 is right, and then camera 1 and 2 is the transformation. So I extract the R, which is identity as advertised. So no rotation, and then transformation. So t-2 actually, this suggests that is other way around, right? So camera 1 in 2 is so left camera in right camera, basically. Right? So and then let's look at x1 and x2. Oops. So x1 x2 x1 x2. So we see So this is x and this is y. So, and yeah, we were discussing that in theory y's really should be, so y goes down actually, it should be exactly the same, but it's not. So such is life. It's just like a tiny little difference in the feature matching. It could happen. And then z is how far away. It has to be 1, so it's sort of by assumption, by definition, we have projected onto the image plane. And then, okay, so we have x 0.5, which is to the right, and then x2 is kind of like a little bit to the right? So there's like this small little difference, and then yeah. So and then this x2 hat, right? So is this, and that's what we have discussed, right? So it's like a, b, c, and so yeah, minus a, b, and c. And then yeah, we can just verify. So x2 hat times x2, all zeros, right? So with some numerical errors. And then we have to make sure a and b are equal. So a is this, b is this. So this really should be 0. And then we try to divide those, right? So we see, okay, is this numerically stable? This is numerically stable. This is numerically stable. This is not really, right? So numerically stable flag only has this. And if you notice, right? So about what we were talking about, this triangle, right? So x1, x2. This is like just like difference between those x coordinates. So this is exactly this, and this is a translation. So this is just back to this triangle, right? So it's like we really you can see how one thing reduces to another, right? So here we have sort of more general solution with some hacks, but those hacks sort of boil down to estimating this exact thing, right? So, and then if you would work out through this geometry and so on, just think more about it in sort of more general case, you will be able to relate all this concept geometrically. But yeah, for now, we just don't want to overcomplicate it. We will just take only this middle thing, and this exactly reduces it to this triangle thing, and then bam, we have s equals 32. So it's kind of far, right? And then let's see some kind of like degenerate case, or yeah, maybe we just like step through the case. Okay, one more easy case, and yeah, here's like a case in which this other thing was good. So this a, right? Really, yeah, it's maybe I should just reject it and just always only take this thing in the middle. Maybe it would have worked better, but yeah, you can see that's like actual division yields very close results for both. So yeah, just keep working on it. Oh, here's a case in which this other thing is kind of trash. So yeah, and then yeah, if you're curious, just work your way through how it's possible to get this minus, right? It's pretty interesting. Yeah, and that's like the naive triangulation. So based on this, we just get a keyframe, right? Ooh, where's my keyframe? Here's my keyframe. So yeah, this keyframe is over here, right? And then we just keep comparing the features that we get to the left image to the of the keyframe, right? So this will get compared to this. Yeah, and that's it. Cool. So next time we work on Gauss-Newton and figuring out the movement of all of those, and just how to optimize, how to figure out where the pose is given the movements of the points in the keyframe. Oh, here's our another keyframe. Nice. All right. That's it. Hope I didn't forget anything. See you.